Okay, and I've said that these potential lines maybe represent the field due to a charge bar here, okay? A finite charge line, a finite line of charge. Maybe it's uniform, maybe it's not. I didn't specify. I said, according to the equipotential lines, I'm going to mark the field vectors approximately to scale at the so-called blue points. These 4 points here are marked in blue. So I'm getting a lot of answers based on the idea that, well, the closer we get to the charge, the greater the field. Okay. So what I'm going to do is I'm going to say, well, I didn't necessarily draw the potential lines accurately for the field according to the equipotential lines. So let's say all we've got is equipotential lines. We no longer have a bar there. Now, how do you determine where the field is strongest? Okay. Well, what are the units of electric field? Repeating what I've said about the introductory problem sets, the very beginning of the introductory problem sets, works out pretty much all the important unit relationships. And they're very helpful for guiding your thinking. So one of the units of electric field, I got this immediately, is newtons per coulomb. Okay. That's fine, but also volts per meter. And volts per meter is the unit concept that allows you to reason this out. Okay. So where do you have more volts per meter? Between this line and this line, or between this line and this line? I'm going to think more volts per meter here. I'm going to think more volts per meter here. Think here. What do you think here? Okay. Up, down. Yeah, more volts per meter here. Why? Because you've got as many volts between here and here as you have between here and here. But you got fewer meters between here and here, or a smaller fraction of a meter, depending on the size of this distribution. You have less distance here than you have here. Since it's volts per unit distance, change in potential divided by the distance, you have greater electric field here, and that's something you really need to understand. And I chose this because in the first place, you had a problem almost identical to this in the homework, and everybody who did that problem did well on it, but it didn't transfer. The reasoning didn't transfer. So when you do these problems, make sure you understand the reasoning instead of just, okay, it looks like it ought to be this because of whatever. So anyhow, you know, what's the direction? What should be the direction that, you know, I didn't give you a point that would really be tested? What should be the direction of the field here? How do you get the direction of the electric field from the equipotentials? Okay, so yep, got a very good answer to the direction in which potential is decreasing. Okay. Now, since I put positive charges here, everybody that drew arrows wanted to draw them away from the positive charges. Okay. And that would actually be correct, but these voltages wouldn't be. Okay. These voltages would have been inconsistent with the positive charges. So when I said according, I didn't write it down, but I said according to the field lines, what should the direction be? Or according to the equipotentials, what should the directions be? Sorry. Okay. So in the first place, it's a good thing I erased that because it doesn't correspond. So if you drew the field away from the positive charge, Yeah, it's natural. That's what I figured you would do. Okay. But it's got to go in the direction opposite the increase in potential. So, okay, well, what should be the direction, specifically, what should be the direction here? Okay. So sketch it for me. Sketch that point and sketch the direction you think the field ought to be in. At a given point, the field, now most people do this things radial because you're used to doing radial, and that's kind of a good habit, but you got to be careful because it doesn't apply when you have a line distribution. Okay. It's got to be perpendicular to the potential lines. Okay, so come back to my example of raise a cinder block, drop it. Okay. Where's potential? Potential increases as you go up, potential decreases as you go down. What's the direction of the field that's acting? Well, it's a gravitational field, which is down. Okay, so you're going to go with, you're going to be accelerated in the direction of decreasing potential. So a positive charge would be accelerated toward decreasing potential. Again, my positive signs in these things were kind of a, now there's a word for what they are, a distractor. Because as I said, the increasing potential isn't consistent with a ball of positive charges. There must be other charges somewhere else. If these are going to be your potentials and you have that configuration, it's kind of hard to think of what one would be. Now, direction at this point. It's perpendicular to the potentials. Okay, well, at this point, and this is kind of lopsided, it's drawn kind of poorly, but it's going to be like so. Right there's the tangent line. And of course, this relates closely to multivariable calculus, also to differential equations. Okay, so there we have it. That could be your direction and your magnitude. Okay. Now, at this point, the direction would be in the direction of decreasing potential. And you're not sure what direction it's going to be, but it's kind of going to be, but you are kind of sure, but it's going to be quite a bit bigger than this one. It's going to be perpendicular. I didn't get the perpendicular, I should be out a little bit more this way, but you get the idea, okay? Here, it's going to be a good bit weaker. And here, it's going to be weaker still. Now, these might be reasonable equipotential lines for a negative charge distribution on a bar. Okay, they start out sort of elliptical, but as you get really far from the bar just becomes a point, and it acts like a point chart, so your equipotentials become circular. All that is worth understanding, thinking about, especially since you're taking two courses where this is going to be really important. Okay. And we're just getting into the multivariable calculus. You don't need the multivariable calculus to do the physics. Everything I've talked about here is the physics. Okay. So take that for what it's worth. We need to move on and start talking about capacitors. Okay, well, we don't want to take time to move the camera to the demonstration. We just demonstrated by using a Wimshurst generator. I can at least show you the capacity. Okay. Okay, we have these two metal plates and they're on a frame and we can move them further apart or closer together. So we had them pretty far apart. And we used Wimshurst's generator to separate charge. It pulled, let's say, pulled negative charge, pulls negative charge off of one of these and deposits it on the other. And I'm not sure which way it goes, because it's not particularly important to me. And because I probably can't remember it anyway. Okay. Then I didn't hold this by hand. So if you do this at home, don't hold this by hand. I attached it to a meter stick and out of abundance of precaution, held it by the other end of the meter stick, even though the meter stick's a good insulator. Wanted to demonstrate a little bit of caution. And then I lowered this in between. Well, what happened? First of all, it was attracted to one of the sides. Why is that? Because, well, let's say that this side is positively charged. Then it's going to pull negative charges on this aluminum strip down into the region. I need three hands here, but you know, down toward this end here, this lower end. And then those negative charges are going to be attracted over here. That's induced charge, and we've talked about that, and you've done problems with that, and you should be familiar with the phenomenon. Okay. So that's fine, but when it finally touches, okay, if this is positively charged, well, the electrons here are being attracted over here, and they're going to be attracted so much that they combine with positive charges here. Okay, to neutralize some of those positive charges, and even more than that, you're going to end up with a net negative charge on the strip, which is going to then be repelled by the positive charge that remains here. This thing has a much less area, surface area than this does. So you're not going to take enough negative charge off of this thing to neutralize all the positive charge on this thing. So it gets repelled, so it bounces over to this one. Okay. Now I'm moving my hand, but you know, the end of the the meter stick was held stationary. It just went from here over to here. And then the repulsion caused this thing now with a net positive charge to be attracted here. So it was repelled from the positive charge here, attracted to the negative charge here. It went quickly from here to here, where it contacted the negative charge here, became negatively charged again. And now it's repelled from here and goes over to here. And each time it goes back and forth, it transfers a little bit of charge, transfers positive charge from here to here, negative charge from here to here. And we keep letting it go, and after a while, it slows down. Okay, so the charge gets distributed, or the charge gets transferred back in the direction of neutral charge, and that neutral charge, or I'm not saying that quite right. A state where these things both have the same charge, so you don't get any interaction. I could explain that with the diagrams, a little hard to do with hand movement. We move the plates closer and it starts bouncing back and forth again. Maybe, okay, it stopped. Okay, at the wider separation, it stops, but you come in closer and there's still some action. Why is that? Okay, well, we can explain all that pretty easily. So if these two lines represent an edge view of the plates, well, Gauss's law tells us that there's a field due to this one. Let's say this plate is negatively charged. And might have I put a positive charge on the other side, that goes on the other plate, that positive charge here. And well, a Gaussian surface through here, and you know what the surface looks like, so I'm just indicating it. You know, surface perpendicular to the plate with a uniform cross-sectional area. If the charge density is sigma, you're containing a net charge of that's equal to the cross-sectional area times your charge density times your sigma. So you get a 4 pi k sigma flux that goes out of this end and into this end. No, out of both ends, I'm sorry, and giving you a field of 2 pi k sigma here, and another 2 pi k sigma in the same direction here, because it's into the Gaussian surface and all that, and you just have to work that out and look at the diagrams. If you understand Gauss's law from chapter before the last one we did, it comes out very simply, and you get a field 4 pi k sigma in between, and it's a uniform field. To the extent that you're not close to the edges of the plates, the field is very nearly perpendicular to the plates so that it enters and leaves the ends of your Gaussian surface. Okay, now perpendicular to the ends and with no flux through the edges and all that stuff. Okay, well, by Gauss's law, you figure out you got a uniform electric field here that's proportional to the charge density. So you got your electric field and it's proportional to sigma. Okay, so if we know the separation of the plates, and I believe your text might use A, the separation. So the separation of the plates is A, then what's the voltage between the plates?
Electric field times A.
Yeah, very good. Okay. Does that have the right units? Well, your electric field is in volts per meter, you multiply that by A in meters, you get volts. That is a potential difference. Or if it's newtons per coulomb, you multiply by A and you get Newton meters per coulomb, which is joules per coulomb, which is your other unit. Okay. So that's good. That's good, right? Good response. Okay, so voltage is E times A. Okay, well, what's sigma? Well, let's postulate a couple of charges. Okay, let's say we've separated a quantity charge of magnitude Q, meaning we pulled Q of negative charge off of this plate to this plate. This being metal, that is what's going on. Sometimes you can pull positive charges, but not constantly. Okay. The plate area is A. got charge Q separated, which means it's kind of stored, right? Until it leaks off, and this thing's leaky, and it's not gonna retain its charge for long. If you come in 2 hours later, you probably can touch it without a shock, okay? Maybe even 10 minutes, I don't know. Never tested it. But it doesn't appear to hold its charge real long, but assuming it holds its charge forever, then you can really say the charge is stored, and at least it's stored for a little while on this particular system. Now, when you design a capacitor for use in circuits, you make sure that it stores its charge long enough. Okay. So you reduce leakage and all that stuff. Okay, well, all that aside, back to what's sigma? Okay, so sigma, well, on one plate it's Q over A, on the other plate it's negative Q over A. Let's say it's plus or minus Q over A, and you know which one's plus, it's the one with the positive charge on it, whichever one that happens to be. Okay. So there's your sigma. Okay, so let's see, what can we do with this? How about we calculate the ratio of stored charge to the voltage? What is Q over V? And this is an important quantity because it tells you for a given voltage how much charge. If this is large, it means you can store a lot of charge without a whole lot of voltage. Okay. So I thought that's a really important quantity. We'll give it a name in a minute, but let's figure out what it is. Not exactly what I was going to do. Okay. We have this over this. Okay. E is proportional to sigma. In fact, E equals 4 pi K sigma. You have the field from this plate is 2 pi K sigma. The field from this plate is 2 pi K sigma. Okay. So this is going to be Q over 4 pi sigma A. And something's wrong here. Let's see. You know, I get one of the most fundamental mistakes people make is confusing upper and lower case symbols. It wasn't making sense because I used capital A for this. Okay. It's E times little a. So I said E times A and I wrote big A. I won't even blame the time change in that because I slept really well through the time change last weekend. Okay. So there we have it. I'm sorry, my bad there. It's this. Okay. Now, what do you get from that? Well, sigma is Q over A, right? See what I did? Not funny. As an embarrassed laugh. Okay, Q over big A over 4 pi K sigma times little a. Well, what else can we do with this? Well, I guess we could write this in a number of different ways. And the way I'm writing it is not necessarily the best, but we want to be really pretty meticulous about our units. It's Q over A divided by 4 pi K sigma, which is big Q over A. Times little a. Maybe should have used a D up here to avoid that confusion. Okay, so there's something wrong with what I wrote down there. Can you see what it is? It's getting a little scary. I've verified myself 3 or 4 more times, but there's no reason to write Q over big A up here. Because I was going to write Q over big A for sigma, which is what it is, charge per unit area. And then I wrote a little a again. So wait a minute, those little a's can't find out. Okay. We finally get big A. Over 4 pi k times little a. Now just take a lesson. At every step, you want to kind of check the dimensions of this thing, check the units, and see if you get units of Q over V. Because that way, when you make multiple mistakes, you can catch them pretty quickly. So I wasn't trying to demonstrate that, but I certainly did demonstrate it would have been a good idea to do my dimensional analysis with every step. Good habit to get into. Even on a quite simple derivation here. So you know, if 1 over 4 pi k is just what we call epsilon naught. Okay. And that's called the permittivity free space. And it becomes important because you get a different epsilon if you have a dielectric. All right, well, that's a poor derivation. It's a good derivation, but done poorly. It really applies to any parallel plate capacitor. So my question now is, I'll estimate that I was generating enough voltage with that generator what's Q if the area is 0.01 square meters? It's actually point. We've got a circle of 10 centimeter diameter. So the squared radius is 0.01 square meter. And you multiply that then by pi, because you have pi r squared. So let's say instead of 0.01 square meter, I'm just going to go with 0.01 square meter. We'll use that as it's an easy number to work with. Okay. It's actually like 0.031416 square meters. But let's just go with that. Okay. Now that would be a somewhat smaller plate. This plate's going to have roughly 3 times the charge this plate would. So what do you get? Well, I like the 4 pi k because I can remember K and I can't remember epsilon naught. K is really easy, like 9 times 10 to the ninth, okay? Newton meter squared per coulomb squared. Okay, it's easy to work out. I also need to give the plate separation. I'm going to give you a plate separation of 10 centimeters. So we have this times your 3 times 10 to the fourth joules per coulomb. Well, you just plug stuff in, you got 0.01 meters squared. K is 9 times 10 to the ninth Newton meter squared per coulomb squared. You multiply that by 4 pi, which is about 12.5, and you get about 1.1 times 10 to the negative 7 Newton meters per coulomb squared. That's just your 4 pi k, and you can work out 4 pi k for yourself. And if you'd rather use epsilon naught, well, if you can remember it, fine. If you want to rely on something you can't remember, that's up to you. But anyhow, it's then times 0.1 meter. That's 3 times 10 to the fourth joules per coulomb. Okay, you're going to end up with reciprocal meters here. You know, meter cubed in the denominator, meter squared in the numerator. Then you're going to divide the joules by meters. And you're going to end up with newtons per coulomb. But then you're going to multiply by the reciprocal of newtons over coulomb squared, which is just going to give you units. The newtons divide out. You're going to end up with the coulomb in the numerator, and the units are going to work. So you just got to get the numbers at this point. And you want to think that when you're doing this, especially when you're doing it early, it reminds you of how things are related. Okay, don't just plug it into a calculator and take the answer and hope that Pearson tells you you're right. Okay, the numbers here are pretty simple. In other words, this is about 1, this is about 1, this is about 1, and this is 3. Okay, so let's just make all these 1s, and now we have a 10 to the minus 7 in the denominator, and let's divide this meter into this meter squared and a meter in the numerator, or 0.1 in the numerator gives you 10 to the 6th. So this is going to be very approximately oh man, real bonehead error there. It's 9 times 10 to the ninth, not 9 times 10 to the negative 9. That ought to be 10 to the 11th. Okay, so again, we got a 10 to the 11th here. We got a 0.1 up here. We're going to get a 10 to the negative 12 coulombs. Which is about 3 picocoulombs. 3 trillionths of a coulomb. Okay. Now that's not a lot of charge. They give you a good shock. Okay. Okay, well, point is, no, this capacitor is not very big. Doesn't have a great capacitance. And since I've been withholding from you, this Q over V, . we call that big C, and I'm gonna write it like this to distinguish it from a Coulomb. You could even write a script C, but we'll go with this. It's charged. I say charge per volt, I should really say charge per unit of potential difference. Okay? But you're gonna think of it as charge per volt, so I'm gonna actually encourage you to go ahead and do that. But remember that volt is a potential difference. Now, if we want more capacitance out of this thing, the simplest thing to do, I mean, 0.1 meter, 0.1 meter separation. Well, okay, 0.1 meter, that's about 10 centimeters, I think, yeah. Okay, maybe a little further. Okay. Now, what happens if I move these down to 0.01 meter, 1 centimeter? What happens to the capacitance? Yeah, it increases. Why does it increase? Because you're decreasing this A in the denominator. It's going to become 10 times as much. Okay. Now, if we charge it with that thing, we're still, if we don't have any charge leakage, going to end up with this many coulombs, 3 trillionths of a coulomb. Now, actually, on this, it'll probably be 100 billionth, because the actual charge on this capacitor, the actual area of this capacitor is about 3 times as great. It's actually 5 times as great. Okay. So, decrease little a, we increase C. And I took a peek at the textbook just to make sure I've done that correctly after all the volume errors. Let me take a look at it again. Yeah, they use D instead of A. I didn't look carefully enough. Yeah, don't have my glasses on, so D looks a lot like A. So, decrease what I call A, what your textbook calls D, and that'll increase C. So if you want to build a capacitor with high capacitance, you want to get the plates as close together as possible. Okay. Now, another thing you can do is get them a lot closer. Okay. Now I can take a dielectric. This is not a good dielectric, but pretend it is. I'll explain what a dielectric is in a minute. You just sandwich this thing around a dielectric. A good dielectric insulates so that the charge doesn't transfer. Okay. And it also enhances the electric field. Now, what's the width of a sheet of paper? Well, 250 sheets of paper, about that thick, right? Okay. How many sheets would it take to make a meter? It will take in the order of 10 of these, probably more like 15 or 20. Okay. But let's just say it takes 10 of these. 10 of these would be 2,500 sheets of paper per meter. Okay. A 2,500th of a meter, only 4/10 of a millimeter. They're not that thick. But anyhow, whatever that is, let's say that's 1,000th. 100th of a millimeter. Okay, so A is 0.00001 meter, 10 to the negative fifth meter. Then your capacitance is increasing significantly, okay? You know, I did another bonehead thing over here. I forgot to multiply this, which is your capacitance. And we get quite a bit more. We get about 10 to the negative seventh. And I'm not even sure about that right now. That gave me my 10 to the negative 12th. And that. If my calculations are correct, and you can correct them, about 100 nanocoulombs would be a tenth of a microcoulomb. That's a lot more charge than I was thinking is on these things. So we'll see. Anyhow, you can work out the capacitance. This would be the capacitance in coulombs per volt. If I decrease this by a factor of 1,000, I'd have 3 times 10 to the negative ninth coulombs per volt. About 3 nanofarads, okay. Units capacitance. Coulombs per volt or farads. A farad is a coulomb per volt. Follow your units. It helps you keep the quantities straight. Okay, well, we're not going to get into dielectric. That's toward the end of the chapter. We'll talk about that next time. I want to talk about the stuff that you're likely to see. And the assignment will be due, I think, tomorrow. So let's just say we've got a source here. Source of voltage. And we have two capacitors. The capacitance C1 and a capacitance C2. Okay. Question is, how much charge on each capacitor? What do you think? Well, how do you get the charge on a capacitor? If you know the capacitance, then you just ask yourself, what's the voltage? Because capacitance is charge over voltage. So if you know capacitance and voltage, you easily find charge. Okay. It's a little clumsy using capital V for the voltage here. So I'm gonna use a small script V to distinguish from capital V. And if I can't keep a capital A straight from the little a, you know what's probably gonna happen, so keep an eye on me, okay? I probably won't make that mistake, but for each capacitor, I'll use V sub cap for voltage of the capacitor, okay? So if we understand this relationship and understand everything that we've done here, then this relationship is really pretty easy to understand. Also in terms of units, coulombs, I'm sorry, coulombs per volt for capacitance, and volts here gives us coulombs of charge. So what is the voltage? What's the voltage across this capacitor? Well, and this is kind of important to remember because we're starting to get into some circuits here. First place, wires are equipotential lines. Okay? Voltage doesn't change across an ideal wire. Now, across real wires, yeah, we're going to measure some of that in lab. Okay? But voltage doesn't change from one point of a wire to another. Until the wire hits something that changes the voltage, of course. Okay, so what's the voltage across this capacitor? Well, from here to here, the voltage goes up. This is negative, this is positive. Wait. Now I don't remember our conventions. This is it's kind of pathetic, but current goes this way, so that one must be positive, okay? That doesn't seem right. Anyhow. V is your change in voltage as you go across here. If you go from here around to here, what's your change in voltage? Zero, because from here to here is just from here to here. It takes no work to get from here to here. By conservation of energy, the amount of work done is path independent. So one path from here to here is just a path that doesn't go anywhere. No work is required per unit of charge to go from here to here. If we go around here, it's got to be no work per unit charge. So the voltage has to drop by V as we go all the way around the circuit. Okay? Now, where does the voltage change? If we follow the path just from here, the most direct path through C1, the voltage can only change at C1. So voltage across capacitor 1 is the voltage of our source. You know, this lowercase v, you can continue to use it if you like. But it makes a lot more sense if I just write this as V source, which I'll abbreviate to VS, voltage of the source. Okay. So you go through the source, your voltage goes up by V source. You go through the capacitor, it goes down by V source. The magnitude of the voltage across the capacitor is the voltage of the source. Okay. So the charge is C1 times the voltage of the source. The voltage across this capacitor is C2 times voltage of the source. If you put these capacitors in a black box, we'll call it a blue box since I use blue, okay? Put these inside of some case, so you don't know what's in there. All you can do is measure how much charge you get for given voltage. And you do that pretty easily. You charge them up with that voltage, and then you discharge them through a meter. Okay, so in the blue box, voltage Vs source charge Q1 plus Q2 equals C1 C2 Vs. So right, C equivalent for equivalent capacitance is Q total over Vs, which equals C1 plus C2. Now, you really want to understand that. You really want to think about how much charge there is on each capacitor, because you're going to get a lot of questions about the more complicated circuits that have so much charge in a capacitor, okay? And you're going to want to think in terms of the charge on each capacitor. Now, let me more quickly do this situation. So now you got voltage of your source in a C1 capacitor and a C2 capacitor. But what you have now is these charges here, charge on this plate, and the charge on this plate have to be equal and opposite. Okay? Meaning the charge on this plate and the charge on this plate have to be the same. Both have the same charge, which we call Q. V1 equals QC1, V2 equals QC2, and V1 plus V2 equals voltage of the source. And that's pretty easy to understand if you think about it. But QC1 plus QC2 is the voltage of the source. Slight possibility of messing things up today. Write down things without thinking. Write it again. If I write it with thinking, this has to have units of voltage. Well, you divide charge by charge per volt, you get volts, right? So C times V1 and C times V2 made no sense at all. They were total nonsense quantities, and I didn't stop to think. So be sure you always stop to think so you don't do what I do. Okay, so that so the voltage across the source is Q over C1 plus Q over C2, which implies voltage of the source divided by the the stored charge, Q is 1 over C1. That equals 1 over your total capacitance. Now, if you've seen the formulas for parallel and series resistance, if these were resistances, this would be parallel. Parallel resistances have the same form as series capacitances. And the reasons are simple. We'll talk about the reasons for the resistance when we get to induction models. Parallel capacitors have the same, the expression has the same form as what you would get for series resistance. Okay. Now, just a quick word of wisdom because we're out of time, but if you have something now that looks a little more complicated, like source voltage, a capacitor here, and up here, parallel combination of two capacitors, then what can you say? Well, you can still say that the voltage across each one of these is the same as voltage across this, because each one of these is connected to the source by an equipotential wire. A wire loses no energy when current flows through it. And, you know, if you got good wires, they're pretty close to ideal. You could even make it more fun. You can put a couple of them in here. And you can put an extra one in one of these and start asking questions. Okay. You know, the charges on these have to be the same. You know, the charges on these have to be the same. And you know, the voltage across this one and this combination and this combination are all the same. And you ask yourself, how is your charge on the capacitors distributed? In the homework, usually you have like 1 volt, 2 volts, 3 volts across the different capacitors, you know, easy numbers. So you should be able to do these with symbols. So there's a start. See how far you can get by Wednesday, because actually you don't have anything due for Wednesday. But I really recommend you get a start. So you understand what we do Wednesday a little better. Okay. And we'll talk about these things and other things. And hopefully I'll set it up so I don't have to do any calculations. No, seriously. Not sure why I had. Sure, actually I did, I know the reason for it, but I didn't.